We have three types of dienes: conjugated, cumulated, and isolated. The most stable is the conjugated because they have resonance. And the least stable is the isolated because in the isolated dienes, there is no resonance in there. Isolated dienes means that dienes, they are separated from each other by two or more sigma bonds, compared to conjugated dienes where the double bonds, they are separated by a sigma bond. Here, these are conjugated, so you cannot move one without moving the other because you do have four p orbitals in there and electrons are delocalized. But in the isolated diene, each double bond is separate. So if we look at the p orbital representation, double bonds behave separate because each of the double bond has two p orbitals in there. There is no connection whatsoever between those two p orbitals because you have an sp3 hybrid carbon in the middle. So this means that if I want to go ahead and break this bond, I can break this bond without this bond being affected. And same thing for this double bond. So all the reactions of the alkenes that we talked about, they do apply for isolated dienes. It depends on how much do you want to use, 1 mole or 2 mole. Do you want to do a reaction on just one double bond, or do you want to do a reaction on both double bonds in there? As I said, isolated dienes, these are the least stable form of diene because the double bonds, they are not connected whatsoever. They are very far away from each other. And it's not necessary two sigma bonds. They can be also more than two sigma bonds. So I can have, for example, this system over here where the two double bonds are separated by 1, 2, 3, 4, and 5 sigma bonds. Cumulated diene, on the other end, these are dienes that are not separated by a sigma bond. The double bonds are directly next to each other. And that is going to force the central carbon to assume a linear geometry with an sp hybridization, meaning that carbon will end up having two p orbitals in there. The p orbitals are forced to be 90° away from each other. In this case, so that they would do an overlap. So this p orbital will overlap with the adjacent carbon, and this p orbital will overlap with the adjacent carbon. Cumulated dienes are less stable than the conjugated dienes, and they are more stable than the isolated dienes. In this chapter, we're going to focus on conjugated dienes, and because conjugated dienes are separated by a sigma bond, we can have a free rotation around the sigma bond. And if we have a free rotation around the sigma bond, we're going to end up getting three stereoisomers in this case. And the stereoisomers, since we have alkenes, so we have E and Z around the double bond. Don't forget that always whenever you have a sigma bond, you do have a rotation around that sigma bond. Sigma bonds can undergo rotation. Pi bonds cannot undergo rotation. Just to refresh your memory in there, if you have just a system of one double bond, and let's say if you have two groups around that double bond, you cannot say that I'm going to do rotation and I'm going to go from the trans to the cis. This doesn't exist, okay? This doesn't exist in there. You cannot do rotation around a pi bond. Pi bond has two p orbitals as we were discussing in there. And these two p orbitals, they overlap with each other. If you wish to change from cis to trans, you have to break the pi bond, twist the molecule so that you can rotate this carbon and make it cis. So rotation does not exist without breaking the pi bond if you have a system of one double bond. But if you have a system of two double bonds, then rotation can exist around the sigma bond. And you can have the trans isomer or the cis isomer in there, or a combination between the cis and the trans. When the groups around the double bond are on the same side. So let's say, for example, if we are considering this double bond here, if the groups around it are on the same side, this is the Z isomer. We can also use the cis since we have two groups that are the same. We have a hydrogen here and we have a hydrogen here. So this is why I can also use the cis. The Z system is more preferred than the cis system. But anyways, you can use both in there. Again, the groups around this double bond, they are on the same side. These are the higher priority groups. So this is why it is a Z. On the other end, if you take this double bond, you have the higher priority groups. They are on opposite sides. So this is why it's an E. Around this double bond, they are on the same side. This is why it is a Z. Because rotation exists around the sigma bonds between two double bonds, then we are going to end up having two possible conformations of the conjugated dienes. And those conformations, to give them a name, we're going to start with an S. So S means that I am rotating the sigma bond between the two double bonds. This is what S means in there. If the two double bonds, they are facing each other, then in this case, this is going to be called S cis. You can do the rotation, and now the two double bonds, they are opposite to each other. Now this is called an S trans conformation. Let's have an example. So if we have a system of two dienes, and let's say if I have a CH3 over here, and if I have a CH3 over here. Now, because the double bonds are facing each other, then this is called an S, and it is a cis conformation. Now, I want to go ahead and do a rotation around the sigma bond. And I want to make it an S trans. So when you do a rotation around the sigma bond, as we did in organic 1, you fix one carbon, you rotate the other, whatever carbon that you want, it's fine. I'm going to go ahead and fix the bottom carbon in here. So the double bond and the CH3 will stay the same. And I'm going to rotate the top carbon. When I do the rotation, always the substituents need to keep the same orientation. So if this double bond had substituents that are trans, when I do the rotation, this double bond needs to keep its substituents trans. So we agreed over here that the bottom double bond, we're just going to keep it the same. We're going to draw the sigma bond in there. And now this carbon, I'm going to go ahead and rotate so that it's going to be S trans in there. But the CH3, since this double bond had a trans substituents, then the substituents need to remain a trans, then this CH3 needs to be over here. And this is now called an S trans conformation. So the rule is whenever you do the rotation, fix one carbon, rotate the other, and the rotation always happens across the sigma bond. Then, when you do the rotation, here I did the rotation of this carbon, the substituents around the double bond need to keep the same orientation. If they are trans, they have to remain a trans. So this is why the CH3 is up over here. Let's have another example. If I have still a CH3, let's say, for example, if I have a CH3 over here, and if I have a CH3 over here, and that is an S cis conformation, and I want to do a rotation around the sigma bond and make an S trans. So now I'm going to fix this carbon over here, so fix it. Okay, so that is going to have the same orientation of its substituents. And then go ahead and rotate the carbon at the top. So this carbon here, I am rotating. Here you go. And if I am doing this, I'm going to end up having my double bond opposite to this double bond over here. Now the orientation of the substituents need to be the same. This double bond had two substituents or has two substituents that are on the same side. They need to remain on the same side. So this means that my CH3 now is going to be here, showing that I do have a cis substituents around the double bond. But the conformation of these two double bonds with respect to each other is called an S-trans conformation. These two are called conformations because they are only involving the rotation around the sigma bond. I did not change the orientation of the substituents. So I am starting here with a cis, and I am ending up with another cis. I am not changing the orientation of the groups on the double bond, so these two are called conformations. On the other hand, if you go from cis to trans, not S-cis, no, cis to trans, something like this. So if you go from cis to trans, we agreed that these two are stereoisomers. Here, there is no way you can rotate from a cis to a trans. You changed over here the orientation of the substituents, not the rotation around the double bond, the orientation of the substituents around the double bond. So these, in this case, these two are considered to be stereoisomers. Sigma bond that connects the two double bonds in there does not behave like a regular sigma bond. A regular sigma bond has this length over here, but the sigma bond between the two conjugated system is shorter. And the reason why it's shorter because of resonance. We said that conjugated dienes are the most stable form of dienes compared to isolated or cumulated dienes. In order to test this, we do a heat of hydrogenation test. So in the heat of hydrogenation, you take your system with dienes and you simply add hydrogen to it. And you see how much energy you are getting out of the reaction. If you get a lot of energy, then this means that your system is not stable. If you get less energy, this means that your system is stable. Conjugated dienes gives the lowest amount of energy compared to isolated and accumulated dienes, and this is why it is very stable.